Okay, well, welcome back to our course on ENGI307 data analysis and machine learning. This is our second lecture. We'll be breaking this up into parts. Last time we gave an introduction going over in general what it means to be doing machine learning. And for this course, we're going to get specific into one area where we introduce this idea of supervised learning. So for this chapter, here is what we'll be covering. We'll give in general, get an introduction to what actually is inductive learning. And we'll be looking at also trying to create hypothesis functions and approximating in the generation of hypothesis functions. In more detail, what we have here is, first of all, we'll give an overview of the design cycle and issues in machine learning. We'll then focus and make sure that we all understand what is meant by inductive learning. We'll look at a concept called Occam's razor and applying it towards what we're going to be doing with supervised learning. Simpler is better. And we want to be avoiding this idea of overfitting. And then as a result, instead of doing this extra training, it gets worse rather than better. We'll look at heuristic search in inductive learning. We'll look at estimating generalization errors. So we start from one and we want to go to a higher general way of and get that performance to be as good, if not better, than what we had initially. We'll look at assessing regression accuracy, and finally look at rate of change ROC curves. So here is an overview of the design cycle and issues in machine learning. So there's 8 steps in the design cycle and issues associated within machine learning. So first is we want to translate the problem into a machine learning problem. So we know what the capability is, but we have to be figuring out, well, okay, how is that going to be specified as a machine learning strategy and a problem? So we want to be selecting the appropriate data. So we want to be using data. So for this supervised learning strategy, we need to have data, and we want to make sure that we have a good data set so we train well. And then we want to get to know the specifics of that data. And so as we do that, we're going to get a better sense of what we should prioritize, what would be factors in each one of those different elements that would be useful for us as we're starting to get a good way for this to be learning. We want to then create a data set for the machine learning problem. And once we're done with that, then we build the learning modules. We start to code that up into whatever mechanism that we're going to be using, whatever type of programming language or whatever type of tools we may be leveraging. Then we assess the learning models. How well did it perform as compared to what we expected with a small exemplary set of data? Then when we've completed that, we're ready to deploy the optimum model and then finally assess the results. So we can see that there's feedback going to each parts of this, but in general, we have those 8 steps that are things that we need to be capturing. So inductive learning. So the task of an inductive learning are the following. So given a collection of examples as we're laying out there for a function f of x. And so we're trying to come up with a model for getting the outputs based on the inputs that we were able to process in terms of function h of x that approximates f of x. So h of x is an approximation. That's what we'll be leveraging. And the approximation function h of x is called the hypothesis function. The unknown true function f of x correctly maps the input space x to the output space y. The central aim of designing h of x is to suggest decisions for unseen patterns. So the better approximation of f of something, f of x, for example, leads to better generalization. Generalization performance is the fundamental problem in inductive learning. off training set error is the error on the points not in the training set, and it is used as a measure of the generalization performance. Inductive learning assumes that the best hypothesis for unseen patterns is the one induced by the observed training set. So that's a little bit of an introduction to what inductive learning, and that's what we're applying for this first strategy in machine learning. So here we have this something called the Occam's razor principle, and the definition is a simpler algorithm will perform better on a test set. So simpler is better, and simpler may stand for fewer parameters, less training time, fewer features, and so forth. Generally, searching is stopped for a design when the solution is, quote, good enough and not the optimal one. Occam's razor principle recommends hypothesis functions that avoid overfitting of the training data. And so let's take a minute to talk about that. And so with increase in complexity, the training set's performance increases, but performance of the test set decreases. And as a result, overfitting has occurred. And so this is the thing that we can start to see that would be happening. So the accuracy of the classifier overtraining examples increases monotonically as the classifier grows in complexity. However, the accuracy over the independent test samples first increases and then decreases. So that's an introduction to some of the basic things that we're talking about in this chapter, but we'll take a break here and then we'll start back in just a few minutes.